Wayne, what's wrong?
It's my flower because got upset to hell on it.
That's fine, Wayne. It's just substitution. That's what we're on to now.
Oh yeah.
We mentioned in part 2 that we're going to do a substitution mechanism, and here it is.
Yep. So first step, we're actually going to write out the full overall equation before explaining how to get to it. With the
Yeah. This would not be the last step in an exam, or actually it might give it to you in an exam, but, you know.
More often you'd have to do the mechanism, then get this.
Yeah.
But to explain it would be more better for you to do the other way.
So basically what substitution is the halogenation of alkanes. So that means we have an alkane, and we have a halogen, so we have methane and we have chlorine.
Get out of the way.
And this gives us the overall equation of this. But we need to know how that happens and how that works.
Yes, we do.
So, to start it all off, we have a stage called initiation.
Do that.
I'll write that in red. Oh, I like it.
Initiation.
Initiation. And this will get started off by homolytic fission of chlorine.
You should remember that with homolytic fission, you've got 2 electrons in the covalent bond. One goes to one goes to the other to make 2 things that are the same, hence the homo part. So
It makes 2 chlorine radicals.
which is represented like that.
And that's the first stage.
That is initiation.
Do you want to take the blue pen?
Yes, I need that. Yeah, thanks.
So,
Propagation.
then we go on to propagation, which is, well, the ball rolling, I guess.
Yes.
So, we have chlorine radical, and we have this. So let's put them together.
CH4.
So you have methane, and it
Also-
encounters one of our chlorine radicals in this chain we're having the reaction in. And what radicals do is they rip something off,
So we
a compound, making the other bit a radical.
They can't rip off the carbon because that would leave 4 hydrogens, which is what it does. It's
Yeah.
going to rip off a hydrogen. Makes that.
It makes hydrochloric acid, and
Another radical.
a radical, which is a methyl radical.
You can see it's lost its hydrogen. It went from 4 to 3. That makes a radical.
It does. Then this flies about, and it can do one of 2 things. It can encounter one of these again, or it can encounter chlorine.
Yes. Because this has already been encountered, you know that in an exam this would have to then encounter the other thing in order to get the full equation.
Yeah.
So we'll react it with that.
It does what it does before, so it makes this up here.
It will take something from there, so it will take one of the chlorines, yeah. CH3Cl.
Leaving another chlorine radical.
So you can see this can actually keep on going, so that might react with that to make another one, carry on and carry on.
This is actually called a chain reaction, and it keeps on going for ages. In fact, until one of our termination steps, which is the last
The next
stage.
step. So I'm going to go with green.
Alright, let's go for green again.
Termination.
Termination. This is the ending of this chain reaction that we're having now.
There's 3 possible things that can happen.
There is 3 possible things, so let's go through.
When this chlorine radical is reintroduced, it can then meet another chlorine
It
radical
can.
flying around.
Making 2 chlorine radicals, so when 2 chlorine radicals encounter each other, they just make chlorine, and that ends the step because chlorine will
It's
not
essentially
really
that in
exciting.
reverse is what's going on when the 2 radicals then meet each other
It is. Then I guess these 2 can meet each other
in the exact same way.
in the exact same way, yep, except they'd make ethene
Yep. You'd have 2 carbons
and 6 hydrogens. And then the last one where these 2 could meet,
CH3,
making what we have at the top here again.
CH3Cl. Like that, and that's termination, so it gets rid of the radicals.
It does
And
get rid of
eventually
radicals.
that will happen.
2, 1.
Yes.
Yeah. I think that's it, that's substitution.
Yep. That pretty much sums it up. The only tricky part in the exam is identifying the overall equation.
Yeah.
You'll know your reactants from the question, it will always give you that, otherwise it's not a question. You know the first radical is going to be from the halogen, so you should know what to do there. Then react that with the beginning, because you don't want to react it with itself, that's just how you'd work it out, you do it with that.
Yeah.
You get the thing that isn't a radical, must be in your thing. The thing that is a radical then reacts with the other thing, and then it gives you the other thing.
Yeah.
And I didn't explain that very well, but you can see what I was doing while I was doing it, so I think that's fine.
There's lots of things in substitution. And I think we should go on.
We should go on to alkenes now.
Alright, let's crack on.
Alright,
Hello.
we're on to alkenes now.
We are. We've talked about it a little bit before.
Yes, the idea that it's a double bond is the difference between an alkene and an alkane.
Yeah.
It doesn't matter how many double bonds there are though.
No,
As long as there's no other functional groups, it would still be an alkene if it had 100 double bonds. Or if it had one.
Yeah.
Which is an idea that Might be new, might be quite obvious, but it might be new.
Yeah.
That idea. We did also speak about the sigma and pi bond, but we'll talk about it again.
Yeah, what they actually look like and why it's the pi bond that breaks.
If we have a carbon to carbon, like that, these each have, and this is from your unit 1,
It is.
p orbitals that sort of look like this, because they're drawn in this sort of shape. And these sort of fold in and overlap over each other
Yeah.
to form a double bond, and that is very strong and hard to break.
It is.
So these are slightly negative, but they merge and make it really, really strong like that. And sigma bond, sigma's like that.
Yeah.
Pi bond, you should know what pi looks like, but sigma bond is present here and here. Pi bond is only present in the double bond, so it's always the pi bond that breaks if it breaks.
Yeah.
And you should know that means that sigma bond is stronger than the pi bond. They're not equal strengths.
If one breaks first, it'll be equal.
Yes.
Yeah.
So this is just a slight development with the idea that it's the p orbitals that overlap. So next we go on to reactions. Let's go on to that now.
Alright, let's do it. Wait, there's lots of room on the board. We could.
Oh yeah, we
speak
can just
now.
do it in one take. I reckon we can manage that.
Yeah, let's do it. Alright.
Alright.
Hello.
So we mentioned
Yes.
that it's the pi bond that breaks. Now let's go on to some actual examples of reactions.
Yes. Now some of these you need to know quite a bit about the reactions.
Yes, which one should we start with? Maybe the one with hydrogen is quite simple, isn't it?
Yeah, let's do that one.
Okay. So if we have, and I'm just going to do the simplest one again.
We have ethene again.
You react it with hydrogen. You're going to form, the double bond's going to break. You're just going to get that hydrogen is replaced. So it's going to be like that.
Yeah.
Except you need to know a little bit
You
more.
did remember some of the conditions you need to know. A catalyst.
The catalyst used when it's hydrogen is always nickel.
It is always nickel.
And at the temperature roughly 150 degrees Celsius.
Yeah, you just need to know that. There's a few things in chemistry you just have to be able to regurgitate.
Yeah.
That's one of them.
And this is called hydrogenation. It has its own word
It does.
for reacting hydrogen with an alkene.
Which is splitting it into an. Okay.
Yes, and now alkenes undergo addition reactions that all follow this form. Where
Yeah.
the double bond is broken and you get two new things like this.
We showed it before, actually.
We did do it in part 2, I believe.
I think it was, yeah.
We did it in part 2, and we said we'll go on to the mechanism, which is actually part 4. We nearly get onto it in this clip.
We nearly
Not
do,
quite.
but they don't do the whole thing, so we'll do it later.
You'll do it later. But they all follow this sort of pattern, and it's something you need to know.
It is.
So if we have, there's another one that you need to know. We'll go on to the water one.
Yeah.
So
So
what I'll do
we have-
up here with that.
Again, we have ethene
And then you react it
with
water.
what state is water in when?
Water has to be steam in this
Yeah.
case. So this has to
Has to
be
be a gas.
gaseous form. Yeah. And that will go to
Just write it underneath. It will go to
carbon.
what was before. Except not.
OH. Well, this hydrogen should be under there, and then like this. It looks like that. I've drawn it really weird. I'll draw the OH down here just to, like
Yeah,
in this
it's a
case
bit
where
more
the
friendly.
hydrogen's here and here. The OH
OH
is
is
here
here,
and the other
and-
H is here.
Yeah.
Sorry, I drew it in a weird way. I'm just used to drawing OHs up here. But
And this one, again, you need to know a bit more about it.
you do. It uses. You don't have to state temperatures this time.
No.
In the exam, it might ask you for an extra mark to say high temperatures and high pressures.
Yeah. You need to know the catalyst.
You do need to know the
again.
catalyst, and it's an acid.
It
You
is.
sometimes get a mark for saying acid catalyst, and then another mark for saying the correct acid
Yeah,
catalyst.
this is a very specific catalyst. And that catalyst
H3.
is.
PO4, which is phosphoric
It is
acid.
phosphoric acid. That's I've got to say it.
It's phosphoric acid. If you do put any other acid down, it will work. So you're normally given BOD, benefit of the doubt, because most acids will work. This is the most
This is the one they
effective.
use.
So if
most of
the
time.
exam paper's being particularly strict, that's
what you
what
want.
to use.
Yeah.
Now,
Okay.
these will also react with HBr, hydrogen bromide, in exactly the same way. Well, H will be here and the Br will be here.
This is where they nearly go into the addition reaction.
Yes. If it's reacting with this simple one that we've used as an example here and here, because it's nice to use an easy example,
Yeah.
it doesn't matter if the H is here and the Br's here, or the H is here and the Br's here.
But if the chain's a little bit longer,
yes, then it does matter.
so if we have, say there's another carbon on, but not another double bond, just another carbon,
It's just like this,
just like that,
and you react to HBr.
then there can be two isomers of what we make.
Yes, because this bit is still just this bit. The H will be here and the Br will be here, or the Br will be here and the H will be here.
And because it's a straight chain, you can only have, well, there are two different things.
Yes.
It either in the middle, or it isn't.
And this gives different names by our naming
It
structure,
does.
nomenclature.
It either makes it one,
One
Br,
bromo, and then
Yeah.
however many carbons there are. In this case, there's 3, so it's propane.
or two propane.
So you've got to appreciate the difference it can make in the isomers it can make if there's a longer chain.
Yeah.
Like I say, in this case, if the Br's here and the H is here, then you can just flip it and that would still be
Still
one
be the same.
bromo.
Yeah.
So that's what you've got to appreciate. And then in the book, they go on to do a mechanism for this. But we're going to go straight onto the over the page, the further reactions,
Yeah.
and do that mechanism. But we're going to do that in part 4, so let's sum up part 3 right now.
Okay.
Go in to get a cup of tea.